Hello and welcome to the second vodcast on the high-level topic of wave phenomena. This one is on the Doppler effect, and these are the 6 syllabus statements that we'll be covering, although statements 4 is about examples and problems which you can do outside of the vodcast. So what is the Doppler effect? The Doppler effect is something you may well have experienced, namely where you can have a source, say a source of sound, but it can apply to any waves. And if you, the observer, are moving relative to the source of a sound, then the frequency and wavelengths of the waves that you detect will be different from those that are actually produced at the source. There's a different perception. Because of that relative motion. A classic example is an ambulance that when it's approaching you goes Nina, 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 but when it's going away it goes Nina, Nina. So Nina, 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 etc. Okay, so what we're going to do today is look at moving a source where it's the source that's moving, as in the ambulance, and a very similar case of a moving observer, and also we're going to look at electromagnetic waves, which require a slightly different approach to other sources of waves. Before we go any further, let's have a look at a couple of examples. Come back here. So here is an example from the University of New South Wales of a moving source. So the bicycle comes towards the observer. And you can detect the change in pitch or change in frequency from the as the source goes past the observer. Okay. Alternatively, we could have the moving observer. So here we have a sound source that's on a stick, and then now we have the video camera attached to the cyclist. This is from the point of view of the cyclist. And again, you can see the change there of the frequency. And here, let's just make that a bit clear. This is the sound wave as detected by the observer. So in 25 cycles, 25 wavelengths, takes up this amount of time, so 8 and a bit milliseconds. When we were cycling towards it, that frequency was shifted. Okay, the number of wavelengths in the same amount of time was shorter, and when cycling away, it was shifted in the opposite direction. So there you have the Doppler effect in action. So to try and explain the Doppler effect, this animation does quite a good job because it shows this sound source wave coming towards the observer, and although it's giving out waves at the same frequency, one wave every 2 seconds according to the source, our detector here will detect a different frequency. Notice how they're compressed before as the source moves through. 4.34, and then it slows away. Now it's only detecting 1.3 waves a second. So the source is giving out waves all the time, but this time the source is moving about half, just over half of the velocity of the waves themselves, the sound waves if this is sound in the air. So it compresses the waves in front of the source and stretches out the waves behind the source. And we can view that. Should we do this one again? It's kind of cool. Does that reflect back? No, it comes from the other side. So compressed ahead. And stretched out behind. Here we have another non-audio source, but here is our source again giving out waves, and here is our observer. And when the two are at rest relative to each other, we spy exactly the same thing. Okay. However, if I move the source, then the waves become compressed in the direction of the source, and we see a definite difference in the wavelength. Steady. And if I move the observer, then the waves either become stretched out if I'm moving away, or compressed if I'm moving towards. Okay, so hopefully those two examples show how compression and stretching of the waves depends on the relative movement of either the source or the observer. Okay, so let's hit the mathematics. For a moving source, then the wavelength of the source will depend, or this car diagram stolen from Hamper, this car is moving forward with a velocity us, okay? And so it's the number of waves of this new wavelength, the wavelength as experienced by this observer the car is moving towards, should be this number of wavelengths, which is the velocity divided by the frequency, the number of waves per second. But because it's compressed into a smaller area, it will be the should be number of wavelengths divided minus the difference caused by the motion of the car. Okay, divided by the number. So that's the change in distance divided by the total distance divided by the distance divided by the car, divided by frequency times time, the number of wavelengths. If we cancel out the t's, we get v minus us divided by f. Now, frequency equals velocity divided by wavelength, so we substitute our new equation for wavelength in here, and we get v minus divided by v minus us over f. Swap that round, so the frequency from the observer equals vf over v minus us. So that's the speed of wave in the medium, speed of sound if it's a sound wave, multiplied by the frequency at the source, divided by the speed of sound minus the speed of the source. That is for approaching. We can do similar maths and for the person who's moving away from, and the only difference is that this turns into a plus sign. So frequency of experienced by the observer equals frequency at source multiplied by the wavelength of the speed of sound of a wave divided by the speed of sound of a wave plus or minus the speed of sound of the observer. In order to decide whether it's plus or minus, the trick is that the frequency always gets higher, the pitch gets higher if you like, if you're approaching the observer. So just think of the situation, if it's approaching the observer, then it will have to be a higher pitch, which will be in this case the minus. Okay, you want the lower number here to give the higher frequency. If it's moving away, it will give you a lower frequency, which in this case v plus u would be a plus. For a moving observer, it's a little bit simpler, and that the frequency is merely the wave of the speed divided by the wavelength, and the wave of the speed in this case is the speed of the wave itself plus the speed of the observer. So this is situation experienced by car number 1 here. Okay, so frequency equals speed of wave combined divided by wavelength. The wavelength itself equals the speed divided by the frequency. Substitute in, and we get that the observed frequency equals velocity plus velocity observer, velocity of wave plus velocity observer multiplied by frequency divided by the velocity of the wave. Again, that comes in either a plus or a minus value depending on whether you're going towards or away from the source. So the summary equation, the same version as given in the data booklet, frequency of wave according to observer equals frequency at source, velocity plus or minus velocity of observer divided by velocity of speed of wave in the medium, in the air. And again, if you're not sure if it's a plus or minus, which gives you the bigger number when they're coming together and the smaller number when they're coming apart. So in this case, bigger number will be plus, okay, when they're coming together. Smaller number when they're moving apart will be the minus. Okay, so that's two examples with sound waves, so they would work with water waves and other such waves. For electromagnetic radiation, i.e. light or radar, radio, then we can't really use that because the fixed velocity of light, okay, with this simple equation here doesn't work. So for velocities which are much smaller than the speed of light, we can use this approximate form of equation. Okay, for velocities that do approach the speed of light, we have to start getting relativistic, but we don't actually need to go into that level of detail here. So this equation, the change in frequency equals the ratio of the speed of the source to the speed of light divided by the original frequency. Going through rapidly, applications. There are lots of applications in astronomy, quite a lot of which we'll look at in our future optional unit on astronomy. But I can give you one quick flash of that. This is a situation with, here you have the Earth, the green dot, and here you have two stars. Now these two stars are very close to each other, and we cannot resolve them as two separate points of light on Earth. But we can look at the spectrum. And here, where we're all in a line, we have these two spectral lines caused by an element. And A is the brighter central star, B is the fainter, more distant star. We'll look at what happens, particularly to the lines from B over time. We'll see that as B moves towards the Earth, the lines can compress towards the blue end of the spectrum. As it moves away, they go towards the far end of the spectrum. So, to get towards, shifted, away, shifted. The narrow lines give the static spectrum, and for A, actually, it moves excuse me, in opposition, and by a smaller amount. So that's a spectroscopic binary, which you can get all sorts of, astronomers can get all sorts of information out of that. Radar works by sending out radio waves and then monitoring their return, and the basic radar just detects whether an object is there or not by detecting the return signal. But more sophisticated radar analysis measures the Doppler effect. It knows the frequency of the waves that it sent out, it looks at the frequency of waves it receives, and from those it can do calculations to discover the velocity of an object. And there we go. So another example of that is speed traps, but a slightly more useful example these days is that of weather radar. So weather radar works by shining radar into weather formations, and by analysing the Doppler effect of a return signal, you can measure the strength of the precipitation and direction of the rain or the snow or whatever it is. So Chicago's getting a bit of rain today by the looks of it. And the final example I just wanted to look at is echocardiography, or use of medical use, where you can measure blood flow, for example, through the heart in this case. I love the music here. And you can see red is moving away and blue is moving towards, so you can measure the blood flow and the rate of blood flow through the heart or different parts of the body. Okay, so that's a slightly lengthy podcast. Oh, thank you. Let's get rid of the terrible music. That's a slightly lengthy vodcast on the Doppler effect, so we know what is meant by the Doppler effect. We can use it using those wavefront diagrams for moving detector and moving source situations. The Doppler effect equations for sound you've now seen. You have to now practice using them, and you have to practice using the Doppler effect for electromagnetic waves using the approximation that we looked at. And we've looked at examples including blood flow measurements and measurement of vehicle speeds. Thank you very much.